Hello, everyone. Thank you for coming. For the sake of trying to be punctual, we're going to start. So happy to see some old faces, many new faces. Welcome to the ICARL seminars. These are a series of invited talks for researchers that are working on autonomous agents, decision-making, AI, and related topics. So this year, we have the privilege of having with us today Razvan Pascanu, who has been working on continual learning and deep reinforcement learning for many years. Although today he's going to be telling us about a topic that is not so much trending, but it's still important, recurrent models. And before entering into his talk, I also wanted to mention that this year we have the pleasure to have two sponsors. For the first time, we have InstaDeep with us, who is our gold sponsor. You have two representatives of them here. They're very kind and nice, helping with us, and they have some stuff for you, I believe, that you can get at the end of the talk. And of course, we are maintaining our relationship with DeepMind as a sponsor of the seminars. So before commencing as well, if you like all this stuff that you're going to be hearing here and want to be also on the topic of, as I said, reinforcement learning, autonomous agents, and related stuff, we have a reading group that is going on Wednesdays in a room nearby. Just feel free to, if you want to join, feel free to reach me or one of the organizers. You don't need to be an expert on these topics. It's just about learning about what's going on in the field. And with all that said, the stage is yours. Thank you for coming.
Thank you. Thank you for having me. Okay, so yeah, I kind of missed a little bit the theme of the seminar. So I'm going to talk about RNNs. So it's not related to RL, but it is sort of fundamentally about the underlying architecture that you might be using for your value estimation or for your policy. So it's the interesting topic, and yeah, I can add a few more of those thoughts at the end of the talk. So before I start, like most of this work is based on this paper. So most of the presentation. So this is work that I've done together with Antonio, Sam, Albert, Anush, Chalar, and Shoham. And this was Antonio's internship project while being a DeepMind. Okay, so okay, so there's some issues in the transfer of the slides, but I wanted to start off like, okay, how did we get here? So we have all of these new AI things, you know, the GitHub, OpenAI Copilot, GPT-4, you know, Llama, so forth. Like, how did we get here, and like, what is behind this product? Like, how do they work? What does make them work? Okay. And I wanted to start with like a bit of history. So I wanted to talk a little bit about natural language, at least the way I see it, of how it evolved over time, and how from natural language we got where we are. And I wanted to start with like this nice quote from Fred Jelinek from 1988. And this just kind of shows you the tension between like linguistics and statistics, and then I will try to make a similar parallel between sort of recurrent models and non-recurrent models in this space. So basically, yeah, maybe this is not really chronologically, but in 1988, you know, you'd get code like this where at IBM, which was at that point like the place to be, you know, they were saying like every time they fire a linguist, the performance of the system goes up. So like linguistics is not really useful at all for natural language. But if you go a little bit back in time, you have so this is a review of a paper from so this is from a paper from 1949, which is as you know, like this is like looking back over time, and they said like, okay, in 1949, this idea of using statistical learning to do machine translation was proposed, and it was immediately recognized as being a mistake. And crude force of computers is not science, and this is sort of the review. So basically, you know, and you keep having this tension, and I would argue that now like linguistics is becoming again more and more important in natural language because we've reached a certain success with statistical models. And now we got to a point where we're struggling to evaluate the system and understand how they work. And it seems, or it is like, we're going to start playing again a role in trying to figure out how to understand this model. Okay, so how does language modeling work, or statistical language modeling? Why did we have this kind of issues? So in principle, in language modeling, what we do is we're trying to model the distribution over sequences of words or letters or tokens, or however we want to partition the sequence. So we want to model P of x1 to xt. And to do that, we factorize it so that we write it as a product of conditional distributions. And then there's something here that happens, which is we're basically truncating this factorization, right? So we're looking at a fixed context and we say, well, this is kind of approximately this. So we're making like a, I'm trying to figure out what an order Markov assumption here. And then, okay, so the idea was that this is how general like language modeling works. And initially the way people were dealing with this is we do this truncation of the factorization, and then we express this conditional probabilities by counting, right? So this is sort of n-grams. And of course, there's a lot more to n-grams than this. This is sort of like a very vanilla explanation, but this is kind of where statistical language modeling kind of started. And then we move towards neural language models, which is sort of what we use nowadays, and like all of the GPT-4, whatever systems are of this form. And the big idea is you look at these conditional distributions and you approximate them with some function. So instead of counting, you just try to model that with some function f of xt. And I just kind of wanted to draw attention to this sort of tension about this nth order Markov assumption. So if you remember like how we derived this whole thing and we got to the point where we are, is we started by taking the distribution over the whole sequence, and then we did this factorization, and then we did the truncation. And then a question that people have been thinking about for a while is like, is it okay to make this truncation? Like, what do we lose? What is that approximate sign doing over there? And then this is sort of as a history, like initially when neural language modeling was a thing, you know, in the 90s, the answer was, well, like we probably are losing something when we're doing this Markov assumption, but there's not really a way around it. And that is because at that point in time, the systems that we had that seemed to be kind of working were basically MLPs, and MLPs need like a fixed input. Right, so it wasn't clear how you deal with like variable length sequences as an input. So yeah, feedforward required this. We had the previous work on n-grams that was kind of successful, so it seemed like a natural assumption to make and an assumption, nice way to go about it. And it was in some sense the only computationally feasible approach that we had. So in the 90s, you know, you couldn't really go far. But there was this, you know, in theory, we had this alternative, which were recurrent neural networks, which did not need to make this assumption. So recurrent neural networks have been around for a while. So they were kind of introduced roughly at the same time as feedforward neural networks. And, you know, soon after we had backprop as the algorithm to train MLPs, we had backprop through time as a way of training recurrent neural networks. I'm not going to go over the details because I want to focus more on the latest nuclear stuff. This is more just the history bit, but I thought it's kind of interesting to go over it. So backprop through time, like you basically just unroll the recurrent neural network and then you apply backprop. So you can, I mean, I think it's a really nice exercise. I don't know how often people nowadays actually try to compute gradients for neural networks by hand to figure out how the chain rule works and how backprop works. But I mean, I would definitely suggest it to at least do it once in your life. It's like a really interesting experience to try to get the gradients by hand. I spend a lot of time trying to figure out BPTT by trying to compute gradients for these kind of things. But the nice thing about recurrent neural networks, or the reason why people got fascinated about them, was this results from Haval Siegelman from the 90s, which basically showed that recurrent neural networks are Turing complete. So they basically, like, if you try to think a little bit of what that means, is they're just a different class of mathematical objects, right? They're not universal function approximators. They can do more. They can approximate any kind of algorithm. They can execute any kind of algorithm. You know, they can exhibit memory and all of this kind of stuff. So basically at that point in time, you know, recurrent neural network were seen as this kind of very expressive architecture that could do anything that we want. In some sense, if you're thinking about AI, AI in some sense needs to be Turing complete. If you're thinking about reasoning, that requires algorithmic execution, right? So you need to have these capabilities, and it just kind of felt natural that what we actually needed were recurrent neural networks. But as you probably everyone knows, like in '94, maybe before that, with the PhD thesis of Sepp Hochreiter, working with Jürgen, we had these results that actually we cannot train these recurrent models. So we have maybe many of you have heard about this vanishing exploding gradient problem. So it turns out that if you try to train these recurrent neural networks with gradient descent, then learning is extremely unstable. So you have, very quickly you get one of the two behaviors: either the gradients vanish or the gradients explode. And because of that, you can't really get them to do whatever you would like to. And this is kind of the main reason why, say in the 90s, and it took quite a little bit of time for people to warm up to recurrent neural networks, was because we believed that it's impossible to train. I think there's a lot of cute things to be said here. I think even what vanishing gradients means, I find sometimes people kind of get confused by that concept, because it's not that the gradient norm goes to zero, it's just certain terms in the gradient go to zero. The other thing that I wanted to touch upon is, I think around this point in time, people have started to talk a lot more and more about memory and recurrent neural networks. And we kind of got stuck with this perspective that if you want a neural or recurrent neural network to be able to correlate two events that happen far apart in the time, then you need for the gradients to propagate from one time step to the other one, right? So, and this is how this vanishing gradients, exploding gradients things work. They look at, basically they look at sensitivity or like saliency maps, whatever you want to call them. You look to see whether, the output at time t, is it dependent on the input at time k by c? If I perturb the input at time k, would the output change? And I just want to clarify that actually this doesn't mean that if the output is sensitive to the input at time k, that doesn't actually mean that you've memorized input at time k. So I always like to give this counterexample. So you have this simple example where I'm just summing numbers. Of course, now if I'm computing the gradient is 1. So basically gradient flows perfectly. So ideally you should be able to know all of these numbers. But if you have the sum, you cannot reconstruct any of the terms, right? So just the fact that the gradient flow doesn't mean that you're actually memorized, but it seems sort of the first hurdle that people faced. And it's kind of, I think now it's kind of ingrained in the community. So every time people talk about memory, they quickly go to this kind of gradient analysis and say, oh, is the gradient flowing? If it's not, that there's no memory. If the gradient flowing is a memory. But just wanted to clarify that that's not sufficient. So just continuing on the sort of history part of things. So we had these results that things didn't work, and then as things move forward, we like there is this kind of community, particularly in Europe, grew quite a bit about echo state networks. I worked on this as well in my master's. So these are basically recurrent neural networks where you don't try to train them anymore. You give up on the idea that you are able to train them. You keep them fixed. You think of them as a random projection, and then you try to learn a linear output. And I'm just mentioning this because it's kind of related with things that comes afterwards, because I think it's within this space that people have started to think a lot about how to initialize recurrent neural networks to have certain properties. And actually a lot of tricks that people use nowadays when they do LSTMs and so forth, a lot of them come from this community and from the works that people have done in this community to understand the behavior of a random recurrent projection. And this is also like a space where a lot of, there was a lot of synergy with like signal processing, and people are trying to understand recurrent neural networks from that kind of perspective. And, you have things like low pass recurrent neural networks, low pass echo state networks, and band pass echo state networks, and all this kind of stuff. So I think that's kind of useful. Then continuing, I'm gonna go through the history a bit quicker, maybe to have time to talk about the interesting models. Continuing with what happened, so after echo state networks, I mean, we had the proposal for the LSTMs from Jürgen Schmidhuber and Sepp Hochreiter. It actually took quite a while. So this was proposed in '97. It's just in 2014 that people really started to warm up to these architectures, particularly because the initial paper weren't, they were kind of hard to parse to a certain extent. They did not kind of show at sufficient scale that these things work. Everything was a bit toyish. And actually the first papers on LSTMs
they did not have a forget gate. And it turns out that if you remove the forget gate, the LSTM doesn't work. So like the initial papers weren't really actually even working. Like it took a while for people to figure out that you need to add another gate here to make it work. But then, you know, in 2014, I have Alex Graves who shows LSTMs working at scale. We have Ilya Sutskever with Oriol and Kwak Lee and others that introduced the sequence-to-sequence model, which is this thing here, which is basically just an LSTM that encodes the text and then decodes it, and it kind of works. It works sort of in a magic way, and it is a recurrent neural network that everyone wanted. So like everyone got excited, and this is roughly the point where like recurrent neural networks became a thing, and you have the GRU and alternative kind of recurrent architectures that kind of blew up at that time. Just to kind of for historical accuracy, the actual first model that got language modeling to work with recurrent neural networks was a Tomasz Mikolov paper from 2010. So this is sort of the first real example when recurrent neural networks were able to outperform an MLP on a fixed context. And then when people really got excited about it. And this is sort of part of this, you know, through this work, like we also have things like gradient clipping, which is kind of fundamental to train any kind of architecture nowadays in order to deal with instabilities. And, you know, in this kind of time space, you know, people start making connections with the ecostate world, ecostate network world, and try to kind of get from their intuition of how they should initialize the models and how they should set up these things. You know, you have things like Ilya Sutskever and James Martin. They propose this kind of multiplicative RNNs, which is again reintroduces, because there's been a topic about these multiplicative interactions. It's been something that's been going on since the 80s. But like it reintroduces this concept that turns out to be fundamental in like modern architecture. So in modern architectures where you have JELU activations, where you have, you know, like in SSMs, like the things I'm going to talk about, you have this thing that people call the H3 block. You know, all of this rely on these multiplicative interactions. And sort of, if we go backwards in time, maybe in sort of like more modern machine learning, this is a place where they get reintroduced, even though they were like a very big thing in the early 90s and so forth in places like Toronto and so forth. Okay, so just to a summary. So what happened is we started with using MLPs because we couldn't do anything else, but people were feeling unhappy about it because you need to make this nth order Markov assumption. So there was this feeling that you are sacrificing something, right? And the whole hope at that point in time was that we were going to switch to recurrent neural networks because they're very expressive. They have this Turing completeness property, but we did not know how to, and we've managed to figure that out in 2010, and then basically LSTMs more or less took over, and then all the language model architecture since then were LSTM based. And you know, this happened at scale. Like Google Translate at some point was based on these LSTM architectures, right? Using the sequence-to-sequence stuff. And then sort of just to show this kind of cyclic behavior that was, you know, this discussion about linguistics and statistical approximation. I mean, this happens in this kind of architecture space as well. In 2016, we have ByteNet and WaveNet, which is like a new architecture. It's not that important. It's basically a form of convolutional neural network. But the thing is, it adds back the nth order Markov assumption. And to me, at least, it's kind of the first paper that argues that, like, look, expressivity is not that important. Actually, what's important is scalability. And we're going to build a new architecture for language modeling that completely ignores sort of this kind of expressivity angle. And then quickly after that, you know, we have, so attention has been proposed. So initially attention was proposed by Dima in connection with recurrent neural networks, and then was heavily exploited in image captioning. So, you know, 2014, 2015, there's like a lot of papers around. I don't know whether they used the word attention back then. I think it was called all kinds of ways, but basically it was attention in a way that's very non-scalable. And then 2017, we have attention all you need, which is the typical transformer that I assume many of you are familiar with, which is kind of like the architecture that kind of took over, at least in the language, but then soon in vision. And, you know, there's been quite a bit of effort to try to get it to work in RL as well. There's been a little bit more problematic, but it is sort of the architecture that everyone was excited about it. And the point of this architecture was, it's not a recurrent neural network anymore. It works on a fixed context length, so it is sort of makes the n order assumption again. It's kind of sort of, you know, in the spirit of like BiNet and WaveNet, even though fundamentally it's slightly different. What it does, it basically treats your context as a set. And what you do every time you need to make an inference, you first have a look in that set and see, is there anything relevant for me? And this is sort of what the attention windows are computing. You can think of it as a, if you want, you can think of it as a kind of nearest neighbor thing where you use kind of a normalized, because of the softmax cosine distance, to figure out which are the things that are relevant to you. You retrieve those and you use those as well as your initial values to kind of make a decision, a prediction of whatever you're supposed to do at that point in time. So this is the transformer, and like currently, as I said, like this is kind of the core component of any of the modern big successes in machine learning that you might have heard of. This is sort of how people usually write this attention thing. So the whole idea is like you're computing these query keys and values. So you use the cosine distance between queries and keys to kind of figure out which are the things that are relevant to you. So, you know, from every state, I don't have the right thing here, but from every state, you're projecting into this query key and value. You're looking at these distances. You put a softmax on these cosine distances to kind of get an attention window. So the attention window, to get the attention weights. The attention weight says how similar is the query and the key. And then you use that to aggregate the value. So to kind of basically retrieve the value. So retrieve the previous tokens, I guess, in the typical transformer language that are relevant for what you're doing. So transformers work really well. Why don't we stop here? And actually, there are a lot of people who think we should stop here because there's a lot of pressure in trying to get these transformers to be like the default architecture for everything. But what are like potential issues with these systems? So one potential issue is that they're not really a sequential model. So they're being developed to work on sequential data, but they really treat your observations as a set. There's no concept of sequentiality in how these observations come one after the other, right? And then, which seems very problematic. This is being resolved or being dealt with through the positional encoding, but like positional encoding has its pluses and minuses, right? So I'm not going to go into a lot of details, but like it's really hard to provide the positional information to a neural network. So you need to have this kind of encodings, but this kind of encodings, they assume that the sequence length is fixed so that you have the right resolution. Otherwise you lose resolution, or you might use information about the topology of the space. So you basically don't know whether 2 is close to 3 in terms of indexes, right? Depending on the encoding that you have. So you either need to keep that information that 3 comes after 2, or you know. So this is challenging. The other thing, based on the discussion that we have, is that it's not Turing complete. And you might ask, why would we care about this? I guess we care about this because we're moving more and more into a space where we're assuming this kind of LLMs can do everything and anything, right? In particular, people talk about, you know, LLMs that do reasoning and all of this kind of stuff, LLMs that do math, but they cannot do that, right? So just as a simple thing, like take any LLM you want, it cannot compute n factorial. And it's easy to show that, right? It's like, okay, if I make n sufficiently large, then in order to execute the algorithm that computes n factorial, I need to do an exponential number of multiplications. But you can look at the amount of flops that the LLM is doing, and that is a constant number, no matter what the value of n. So obviously, it cannot execute this algorithm, right? But at some point, it doesn't do enough flop computations to actually execute n factorial. It might guess the answer correctly somehow, but obviously, it cannot execute the algorithm behind it. And take any algorithm that has a complexity that's worse than linear in the sequence length, like LLMs technically cannot implement those algorithms because of how they're built, right? So you know, this kind of like Turing completeness, or this ability to approximate algorithms potentially is important if we do think this is kind of the architecture that will do everything. Maybe we don't want to do that. Related to that, we cannot provide guarantees, and this seems to be kind of important, right? At the moment, we're relying more and more on these architectures to do all kinds of things, and we want to have certainty that they do what they're meant to, right? If tell the LLM to, I don't know, solve some equation, I'd like to know that it's actually trying to solve that equation. I like to have some kind of guarantees that it's trying to do that rather than it's trying to guess the result, and somehow it got the result okay for a lot of examples. And this also becomes important when we talk about like OOD generalization, because like that's kind of the direction we're moving, and there's a nice connection to continual learning and all this kind of stuff there. The other thing is that kind of now going more closer to what I'm going to talk about next is sort of the transformers rely on softmax. So if you think of how the architecture works, is you have all of these projections, but inside the architecture, you end up having multiple softmaxes. So each block has its own attention, and the attention has a softmax. And softmax is a horrible activation. It's a kind of activations you never want to have in your architecture, because you have a lot of issues with it. So softmax likes to be unimodal and likes to saturate relatively quickly. And once it does that, then gradients do not flow through the softmax. So you can't really learn it anymore. So you can think of it as some kind of form of loss of plasticity, or whatever you prefer to call this. If you apply softmax over something that's extremely high dimensional, then the credit assignment becomes really hard. So you'd start with something like uniform, and then actually when you try to compute the gradients on everything, that gradients vanishes pretty quickly. So it's really hard to do this kind of credit assignment problem. But then the fifth point, and this is sort of my entry point to the new recurrent neural models that I wanted to talk about, is they're actually expensive. So the only reason they seem to be fashionable and the right tool for a lot of things is because you can parallelize them very well. And then that's what people usually rely on. So when you run these huge systems, and here by like 30 billion, 300 billion, whatever systems, the only reason we can run systems of that size and we can train systems of that size is because we can heavily parallelize everything that's going on there. But if we would not rely on the parallelization, they're actually extremely slow. In particular, every time you're trying to make a prediction, your cost is linear in the context length. So, no matter how far in the past you want to look, like the number of computation you have to do is proportional to that. And that becomes really problematic when you're trying to do like, nowadays when you're trying to use context of like 32K, 64K tokens or things like that, right? So those are huge numbers. So this becomes quite problematic. There are tricks you can do, but those have all kinds of problems as well, like key value caching and all this kind of stuff. So what's happening? Well, recently there was this S4 paper, and this is basically the thing I wanted to talk about. So was introduced again, and what is this? This is basically a recurrent neural network. And in my talk, I'm going to try to convince you that this is a recurrent neural network, and I'm trying to say what is the innovations that kind of made this recurrent model work again. So again, we have this kind of cyclic behavior. For a while, we kind of got very excited about recurrent neural networks, then we decided they're not good anymore, and now we're kind of slowly but potentially moving back towards looking at them again. Okay, so how this whole thing started? It started by people making this long-range ARENA benchmark. So this was supposed to be a test for transformers and variants of transformers, and it was supposed to test how well transformers can actually deal with very long sequences. And then it turned out the transformers were really bad at it, like most kinds of transformers. So these are all kinds of variants, and none of them are really doing anything meaningful. And then in this paper S4 that Albert did, he introduces this new architecture that suddenly was doing considerably better than everything else, right? So it jumped into the 90s. So this is sort of our starting point. So this is where I got interested in this research direction, and I was like, okay, what did they do? How did they make this huge jump, right? Whenever you see a jump of like 20% or whatever improvement, that there's usually something there, right? Like you don't get this kind of improvements. So it's worth putting some time into it and understanding what is the fundamental difference that did that. And if you look at the SSM papers, and I encourage you to do, if you kind of get interested in this kind of architectures and you're interested in decision making when you have like when you need to rely on long context, like you might need to rely on this kind of architectures. The original S4 paper, it's actually quite hard to parse. It starts from like continuous state space model. So you have this continuous time system. So you have like an ODE here that derives how things are going, and then you try to do some kind of discretization of that system to get exactly the model that it works. And you have all of this like weird initialization that relies on like orthogonal polynomials, and there's like just a lot of math. And basically, it's not clear what exactly the system is. So like if you open the paper, you know, it's a really cool paper, especially if you like theory, but like you're faced with a few pages of just math that you need to go through it to kind of see what's going on. And this S4 layer, the other thing that seemed kind of interesting was basically thrown in as a replacement of attention. So instead of just being used as a recurrent neural network on its own, it was plugged in into these typical blocks that you have when you do transformers. So you have these blocks where you basically push your data first through. Usually this was the attention, now it's replaced by S4, but then this thing is followed by an MLP, and then this forms a block, and then you repeat this over and over again. And there is a lot of other detail here, like layer norms, keep connections, dropout, and so forth. But I'm kind of like, just to make the drawing a bit easier, is like you have this pattern, this block, this paradigm that transformers heavily rely on, and S4 just basically used the same pattern, just swapped in the S4 layer instead of the attention layer. And then the other question that we had was, okay, to what extent is the S4 layer itself that made a difference? To what extent is the reuse of this block, which people don't typically use? So you never see like an LSTM used in a format like this. To what extent is the block itself important? And then also, like, there was just an explosion of papers on this topic. So we're like, okay, we need to look into this, and we need to understand what's going on here and see whether we can figure out what are the main differences that made these things work. Okay, so the key insight when you start looking into this, so you go through all of those pages of math, you end up at the end, this is kind of the formula that you use in order for this system to work. So if you look at this, and for people that are somewhat familiar with recurrent neural networks, this is just a recurrent neural network, right? So the formula looks identical to a recurrent neural network with the note that it is linear. There's no nonlinearity here, but it's a recurrent neural network. However, this recurrent neural network is very weirdly parameterized. So because it comes from this discretization process, if you look at the weights, the weights have the form of like exponential to delta times A. Delta is sort of the time step, and something that you have to learn. And then the B matrix, has this A inverse, and sort of from this polynomial, optimal polynomial literature, you get that A has to be initialized with numbers of this form, like 2 to the n to the power 1/2. Like all of this looks very complicated and weird, and it's very non-machine learning like, right? We don't typically initialize neural networks with this kind of things, right? This seems a very precise kind of initialization. So we wanted to understand to what extent does this weird parameterization or this kind of initialization play any role in why the systems work. And how do we do this? We started with vanilla RNN, and then we tried to figure out what we need to change for the vanilla RNN to make it work. So what we did when we started this project, we took the block. So we said like, okay, let's keep the block because maybe there's something about this block. Let's keep the block and just replace, the same way the SSM folks replace the attention with an S4. Like, let's replace it with a normal RNN. This will be the typical formula for our RNN. This is, it's been the same formula since the 80s, more or less. So this is the vanilla RNN that everyone would kind of use. So like we say, okay, let's drop this bit in here and see what happens. And when you do this, like, normally, the RNN has this non-linearities. It's like fundamental to the RNN literature is like you need to have this non-linearity. So you have a choice of the non-linearity, and we use sort of typical non-linearities that you'd use for RNNs, like 10H. And then we try sort of the linear, we try the linear RNN as well, because S4 behaves like a linear RNN. And first observation was the linear RNN works very well. And I think to me, this is maybe the biggest insight in all of this S4. So if there is one thing that you can get out of all of this talk is that actually you don't need that nonlinearity. And it took a really long time for people to understand that you don't need that nonlinearity. Because the thing is, if you look at all this kind of like expressivity things, like the nonlinearity is fundamental to get those results. And it's the same, like assume you take an MLP and you remove all the nonlinearities, right? It just becomes a linear map. It's completely non-expressive. So like the idea of removing nonlinearities is extremely counterintuitive. And actually it's a very interesting question of understanding why can we get away with removing the nonlinearity? And the reason, and we had like a little write-up on this, the reason for that is actually this block. So the linear RNN on itself doesn't do anything. It's a horrible model, and you shouldn't use it. But if you have a linear RNN in a block where it's followed by the MLP, it turns out that you can actually recover the expressivity. So it turns out that you get this very interesting behavior where the linear RNN is just trying to compress the sequence of observations that you have, and the MLP takes over all the nonlinear processing. And you can prove to a certain extent that you recover the expressivity of a nonlinear RNN. So this kind of paper is trying to argue that actually if you have a linear RNN plus a pointwise applied MLP, then you get the expressivity of a nonlinear RNN, and that's why we could get away with using it. But then the question is, why would you? Then, like, what is the benefit? Sure, like you can get away with it, you have the same expressivity, but why would you want a linear RNN? And there's multiple reasons for it. So one reason is, well, you can diagonalize the system, and that can make it much cheaper. So when you do this diagonalization, unfortunately, because you don't know whether the A matrix is symmetrical, you end up with complex numbers because your eigenvalues can be complex numbers. So that's the price to pay. So you end up in this weird world of complex numbers, but otherwise you can diagonalize it. And now you don't have a full matrix. And with small caveats, you don't lose anything in terms of expressivity. And once you have a linear RNN that's also diagonalizable, you can realize that actually you don't need to run the RNN in sequence, right? You can now cheat and parallelize because you kind of know what the output it is, right? So you can take any sequence, you can split it into subsequences, run those things in parallel, and then you have a way to compose them to basically get the correct answer. So the gains that you get is, you get efficiency, considerable efficiency. And I think this is something that's important to note, because if you look at the like LSTMs versus transformer, it's not necessarily that the LSTM works worse than the transformer. It's just that the transformer, you can train it 10 times faster or like 20 times faster. And I think that's where the big success of transformers is. It's sort of in their ability to train them very efficiently. And if you do a diagonal linear RNN, then you get a similar efficiency. So this now kind of trains at the same speed as a transformer would. So you get this kind of 15 to 20x speed up by just diagonalizing. The other thing that you get is controllability of the system, right? So we talked about exploding vanishing gradients. So this comes like mathematically when people try to do this analysis, you end up basically analyzing the Jacobian of the transition function that goes from time t to time t plus 1. So you need to compute the Jacobian, and you need to look at the eigenvalues of the Jacobian, and depending on how those eigenvalues, depending on those eigenvalues, the system is either stable, unstable, or things like that. But the issue is that the Jacobian depends on the observations that you have, and it's not something that you can actually compute efficiently in closed form and then work with it at training for a normal RNN. But if you have a linear RNN, well, that Jacobian is just the recurrent weights, and your recurrent weights are now diagonal, so you directly have access to these eigenvalues. So it becomes trivial to control the system, and it becomes trivial to ensure that those eigenvalues, for example, say smaller than 1, which is in magnitude, which is sort of something that you need for the system to be controllable. So in particular, like you can come up with parameterizations, and you can come up with the parameterization that you like, but this is sort of a parameterization that we used. You can come up with parameterizations like this, where basically, if the parameters that you're learning are lambda r and lambda I, like no matter what values for these things you give, like the system is stable. Like by construction, the system can only express linear RNNs that are stables and are trainable. So you don't need to worry about that anymore. So you don't have this kind of exploding problem that you need to worry about. The other thing is you can control initialization quite well. Okay, so I have a bit of time. So you can control the initialization quite well, and this is also quite important because sort of that's where the success or lack of success of a system in deep learning more often than not stands in how well you initialize your system. So whether you're doing RL or you're doing whatever, like if you in order to get a neural network to train, like initialization is a big part of it. And there's a lot of issues that you can solve by just dealing with the initialization. And again, here, you can do similar things. So in particular, what happens is the magnitude of the eigenvalue actually tells you how quickly information disappears from the system. So if I think of this you think of it as a moving average, right? Think of the eigenvalue as being like the coefficient of your moving average, right? So if that coefficient goes close to 1, then you have a long memory trace because of how you average anything. If that coefficient goes close to 0, then you're going to forget things very quickly, right? Like basically that moving average is only going to keep track of the last few observations that you had, right? So now you have a good sense of how to initialize these eigenvalues depending on the signal that you're trying to model, depending on the data that you want to model. So if you need to have long memory traces, then you want all your basic eigenvalues to be concentrated on the surface of this circle, right? Because that's where the magnitude is close to 1, right? So this is the complex plane. So because they're complex numbers, so you're now working on the circle. And if you're on the surface of the circle, then basically that's eigenvalue equal 1. Then you're basically just summing everything. So you're not throwing any information out. If you're too much inside, then you're going to have a very quick decay of memory. So information is going to vanish very quickly. So now you can control this quite nicely at initialization. And this is another benefit of working in this space. The other benefit is that you can control the phase of the signals that, like you can think of each point here as being some kind of sinusoid. Actually, there's a lot of connections in trying to understand these systems and Fourier transforms and stuff like that. But like the other thing you can control is like where on this ring or whatever these things are called, torus, like where are you going to sample your points? And by controlling that phase, again, you can control how the behavior of the system. And actually, this turns out to be quite important in certain long-range problems. It seems to be quite important not to kind of spread all over, but to focus your eigenvalues in like a small corner of this thing. The other thing that is becoming interesting is the closer you are to the surface of the circle, the more sensitive the system is. Because if I'm thinking of a moving average, if I have a coefficient on 0.99 versus 0.995, it makes a much bigger difference compared to 0.9 versus 0.905, right? It's just sort of how these things work. So you realize that actually you need to have a lot more resolution when you get close to the circle, because that's where all the every small change here makes a big difference, and you need a lot less resolution as you go back to 0. So then you can come up with a new parameterization, and this is sort of the double exponential that we use here. All it does, it basically says, the closer you get to the circle, the smaller the steps you're making. So it's like, think of it as like changing the geometry of the space, right? And you dilate the space close to the surface of the circle, and you contract the space close to the 0. And this kind of helps learning quite a bit, because now you can explore much better eigenvalues that are very close to 1. The other thing that you realize is that, well, this is not like we a lot of time when we think about this, we think about it from a dynamical system point of view, and we think of it as a normal dynamical system, but you have an input, right? So the input gets fed in at every time step, and the system can become unstable because of the input. So therefore, like the final step in what we've done was providing a normalization of the input to make sure that the input itself does not stabilize the system. And basically all that means is like now the magnitude of the input somehow needs to be a function of the eigenvalue, because if the eigenvalue is very high, then the input is more likely to stabilize the system. If the eigenvalue is low, then you don't need to do anything to the input. So you have this gamma that somehow is a function of the magnitude of the eigenvalue. I mean, you can look at the paper to see where these formulas come from. It's not the only normalization that you can do. Like you can come up with a normalization that maybe is more intuitive to you, but like for us, it turns out that this normalization makes a lot of sense, and it's derived from first principles. So if you look in the paper, there's like a nice story behind it, or like the kind of assumptions we make. So basically, whenever you do the normalization, you need to make an assumption on your signal, of like how your signal behaves, and this is the result of such assumption. So you put all of these things together and you get sort of what we call this linear recurrent unit. And this is sort of our variant of like SSM. And this is, I don't have it here. But this linear recurrent unit now kind of performs the same as S4, but in some sense, it's a lot simpler. And I'm going to have another slide where I'm going to summarize the main findings. So there's kind of like 4 things that you need to change to an RNN to make it work. I'm going to restate them so that we make sure that everyone kind of gets a sense of what they are. But basically, this I mean, you have to kind of believe me, but this linear recurrent unit is considerably simpler than if you try to parse the original SSM models like S4D, S5D, and so S5 and so forth. And it also kind of shows that all of these systems, even though they're introduced as some kind of like continuous state space models, they're basically just some form of recurrent models that don't have a nonlinearity, that are linear, and that's sort of what makes them work in connection with being used in this block where you have the MLP. The other the other thing that I wanted to make is maybe, okay, I've been through all of this, so we've been trying to convince you that like now we can get these RNNs to work. The other question maybe is, what is the relationship between these recurrent neural networks and transformers? Like, is there anything we can say about the relationship? And actually, there is something we can say. And to introduce that, I'm going to start from this paper that's coming from Tomasz Mikolov, so Simpletron. I mean, there's a lot of other papers that make similar claims, and it's kind of something obvious once you start playing with the transformer. It just feels like something natural to do. So if you look at the transformer, so how does the transformer work? So you have your input, where over this axis you have the input sequence. So you convert this into a bunch of values, keys, and queries. And now, if you look at one time step, what you do is you basically compute you take your query, you do the cosine distance with respect to your key. So you do dot product between the query and key. So you compute this for every pair in your sequence. And then you get this big matrix that's yellow here, that is sequence length by sequence length. And then you apply a softmax. So this what the softmax does is sort of a normalization. So I have these distances. So this is the distance of query one with all other, I don't know if I got the dimensions correctly, but query one with all other possible keys. And then I'm applying softmax, and the softmax is going to normalize these distances. And once I have those, I can multiply them with the values and then sort of get sort of the output of the attention. So that's how it works. But what this paper claims is like, well, if we would drop the softmax and then we have linear attention, what happens is actually, you know, this is just a series of multiplications. We don't need to multiply things in this order. We actually can change the order which we multiply things. So we first can multiply the key and the value, and then we can multiply this by query later. And the advantage in this paper they talk a lot about is sort of moving from a L by L matrix to a D by D matrix, which can be much smaller. But the other thing that you can realize if you think of this as causal, like if you're doing this attention in a causal way, is that actually you can do this recursively, right? So, you know, you start with some D by D matrix. So every new token that you have, you basically all you need to do is you need to do this rank one correction to this D by D matrix, which just includes the observation that you have at this time. And every time you want to resolve this linear attention, all you have to do is take your query and multiply it with this D by D matrix. So I can go over this again for people who are really interested in this, but what I was trying to show here is that actually, if we allow ourselves to get rid of the softmax, then we can rewrite the computations of a linear attention, and they start looking a lot like a recurrent neural network. And actually, there is this paper, this recent paper by yes, Joan Sacramento and others. I forgot the name of the first author, but there's this recent paper, Gated Recurrent Neural Networks, and they try to make this mapping one-to-one very explicit. So basically, if you want to have a relationship between recurrent neural networks and transformers, well, linear transformers are a form of recurrent neural network. So that's the connection. And the separation comes from that softmax. And then sort of the big open question is, what does the softmax do? It seems like it does something magical. We just don't fully understand what it does. Okay, so what is the summary of what I was trying to say here? So this LRU model I've introduced is basically just a recurrent neural networks. What did it take to make it work? Well, first of all, you have to have linear recurrence. And this is important for two main reasons. One, it makes things scalable. Second, you can control the recurrent system perfectly. So you can make sure that things don't explode. You can control how quickly information vanishes from the system. Everything you can control in closed form, trivially, without any computational burden, right? So because it's a linear system, like we can do a lot of analysis and we can understand the system quite well. And we can parallelize it extremely well. We can diagonalize it, and then we can parallelize the whole thing, and it can run extremely fast, 20x speed up over a normal RNN. But then if you do this, if you do a linear recurrence, then you need to stack it with MLPs. And that's the only way you get back expressivity. Without this, you don't have an expressive system. And then the other things that we did there, like they might be less or more important, but they're more on the like how do you parameterize this linear RNN such that it always stable, so that it's kind of useful, because otherwise you need to do a projection step to stay within the circle, so you know the system is so these are like smaller things, but they're of course important to make the system work, but they're like kind of just follow-ups. These are the two important things. This is the main change that made SSM work now and get RNNs to work again. These other things are just sort of natural things that come once you decided to make these two steps, and now you're trying to run the system. You basically are forced to do these choices. You know, you're forced to parameterize this in a stable way. You're forced to use a double exponential if you want to have this kind of change in resolution of the space, and you kind of have to have this rescaling. But I think it's kind of interesting now that we kind of went through all of this to kind of think back and try to figure out what happened. So one question is like, okay, now we've got recurrent models to work again, and I mean, I haven't filled up the slides with numbers, but like I can kind of trust me that now these SSMs, like, you know, they perform on par with transformers. Now the question is, initially we were talking about we want to do RNNs because they're more expressive, they have this Turing completeness and so forth. So one question that one could ask is, are these systems Turing complete? And we don't have an answer. This is a very new architecture, like no one's spent the time to try to figure these things out. But my gut feeling is that no, we sacrificed Turing completeness at some point in time. We're never getting it back. And actually, it's an important, it's an interesting question of if we ever had systems that were Turing complete. Because my argument is, as soon as you try to make the system to be learnable, so you try to make it stable, then you're reducing the things you can represent of your model, because you're now enforcing the recurrent ways to be in a particular part of the space. And that basically doesn't allow you to represent, like, you know, it removes the Turing completeness of the architecture. If you have, you know, if you add this restriction on the weights, basically the system is not Turing completeness. So I think, you know, early on there was a lot of emphasis on the expressivity of these models. It's not clear if we got them back. We did get back sort of the elegance of having a recurrent network and the compactness and sort of the niceness to work with recurrent neural networks, but we maybe have not recovered this fundamental property that we thought was so important. The other thing that I think is important to understand, and I think it's relevant anywhere, is that, like, it seems that scalability is actually quite important. And if we're looking at architectures and which architectures survived over time, usually the architectures that bet on scalability is the ones that are still around. And architectures that try to like make things overly complicated are the ones that kind of died out and became like not used anymore. The other thing that I didn't put it here, but because a lot of you guys are interested in RL, the other interesting thing about this model is actually RL. So I don't know how many of you have tried to use transformers in RL, but they're like a pain. You can't really run, and particularly like if you do online RL, transformers seem unable to learn in online RL. So there's some papers that are trying to argue that there's ways of making it work, but trust me, it's really hard. So the advantage of this is actually you can probably use the systems in RL relatively well. And the reason for that is because the way the memory of the system works comes from this recurrence. And actually, a lot of it comes from the initialization. Like you kind of decide on your memory traces when you initialize those eigenvalues. And it's not clear to me that learning actually does much. So you can potentially even freeze those weights, not really learn them, and just focus on learning the MLPs. So then like all of this kind of weird interference that you get in transformers when you're trying to learn the attention in RL, I'm almost sure you don't have it here. And if I'm not mistaken, there's like a paper or two that try to apply the SSMs and they managed to apply them successfully in online RL. So like if you're thinking about decision-making where you have to rely on very long sequences and you want to condition on very long sequences, this could be a good architecture for that. So with that, I want to thank you. And I just put on the slides the two things that I'm organizing in case anyone tends to be interested. So this is a summer school that I think is great. So anyone who is interested in summer schools, I urge you to check the websites. The new summer school is not up there, but it's going to be up there. And POLAS is a conference on continual learning. And I heard a lot of you people are interested in continual learning. So consider looking up the conference and consider applying to it. So it's going to be in Italy next year. So it's going to be close. Cool. Thank you.
Thank you. We're going to have to leave soon, but there is time for a couple of questions. We can keep talking at the networking session, but if you have something quick to talk, to ask. Do you want to do it now?
Yes.
What are potential use cases? What do you think will perform well in real world?
So can you?
What are potential like use cases for this?
Right. So like the papers have tried these systems in a lot of things. So I think like speech, for example, which is going to work really well. Particularly like if you go back to SSM, it allows you to change the sampling rate and then able to deal with that, which is actually quite interesting. So speech works, it has been applied to biological data, to, like I forgot exactly what, some kind of sequential biological data, and it was argued that, I want to say DNA, but I don't think it was DNA, but it was, they argued that it worked really well. Language is another, so there is a WRKB, there's a system maybe you guys have heard, is one of these chatbots that it's open source and it kind of works. It's basically this, more or less. It is their own variant of this, but it's in this family of like linear RNNs as well. So we know that it can work extremely well in language as well. So these are all applications. And again, I think it hasn't yet been explored a lot, but I think RL is definitely a place where it can make a difference because in RL, we don't have really good models to deal with long sequences. And if these things turn out to be learnable in an online RL, because for offline RL, transformers work, but for online RL, they don't. Any other?
If not, I mean, I have questions, but I can make them later. So let's wrap up now because we need to leave. Thank you for coming. As I said.